Hello everyone, my name is Santosh and I am a student of BSc Chemistry Honours first year. It is a presentation video on physical chemistry topics. Entropy, the property which is used to measure the degree of randomness or disorderliness of a system. The greater the randomness, the higher is the entropy. For example, crystalline solids have perfect order arrangement of the constituent atoms. Liquid have more entropy than the solids. Entropy is an extensive property and it is also a state of function. Entropy change. The change in the entropy during a process when a system undergoes a change from one state to the another. Delta S is equals to S final minus S initial. For a reversible process at equilibrium, the change in the entropy is expressed as delta S is equals to Q reversible upon T. Delta S is defined as the amount of heat absorbed by 1 mole of the substance isothermally and reversibly divided by the absolute temperature. Unit of delta S is joule per Kelvin per mole or calorie per Kelvin per mole. Entropy of fusion. Change in the entropy when 1 mole of solid get converted into liquid at a particular temperature. Delta S fusion is equals to delta HF upon TF. Entropy of vaporization. When 1 mole of liquid get converted into the vapors at particular temperature. Delta S vaporization is delta HV upon TB. Entropy of sublimation. When 1 mole of solid directly get converts into the vapors below their melting point at a particular temperature. Delta S sublimation is equals to delta HS upon TS. Factors affecting entropy of system. Volume of substance, presence of impurity, temperature, pressure and mass. State function. The thermodynamically property which depends only upon the initial and the final state of the system and independent of the path followed by the system. For example, temperature, pressure, volume, energy, enthalpy, entropy, free energy, etc. Path functions. The thermodynamically property which depends upon the path followed by the system. For example, work, heat capacity. Conditions for the state functions. It must be exact differential. Their cyclic integral is 0. It must follow the Euler's theorem. To show that the entropy is a state function, if entropy is a state function, then ds must be the exact differential. We know that ds is equals to C dt upon t plus R dv upon v. At constant temperature, dt is equals to 0 and thus equation first becomes ds is equals to R dv upon v. ds upon dv integral t is equals to r upon v. Differentiate the above equation with respect to temperature at constant volume. We get delta square s upon delta t del v up from limit from tv is equals to delta upon delta t bracket r upon v and limit from v is equals to 0. Del square s upon del t del v limit from t is equals to 0 gives second equation. At the constant volume, dv is equals to 0 and thus equation first will become ds is equal to C dt upon t. ds upon dt will be equal to Cv upon t. Differentiate the above equation with respect to v at constant temperature. We will get ds is equals to C dt upon t plus R dv upon v. At constant temperature, dt is equals to 0 and thus equation first will become ds is equals to R dv upon v. ds upon dv from limit t is equals to R upon v. Differentiate the above equation with respect to t at constant volume. We will get d square s upon dt dv from limit t is equals to 0. At constant volume, dv is equals to 0 and thus equation first will become ds is equals to C dt upon t. ds upon dt will become equals to Cv upon t. Differentiate the above equation with respect to volume at constant temperature and we will get d square s upon dv upon dt bracket is equals to 0. Compare the equation second and the third. We will get as ds is an exact differential, hence entropy is a state function. It tells about the entropy of the system. It tells about the reversibility of the process and it tells about the efficiency of the process. Second law of thermodynamics. It states that all the naturally occurring processes are the thermodynamically irreversible. For example, cup of tea cool down after some time and it can't become hot by itself. The naturally occurring process cannot be reversed without the help of any external agency. The heat energy cannot be completely converted into work without leaving some change in the system. All the naturally occurring processes causes a net increase in the entropy of universe. The entropy of universe continuously goes on increasing towards the maximum. Carnot cycle. given by Sir D. Carnot in 1824. The working principle of all the heat engine is same. The working substance is a fluid, for example liquid or gas or vapor. The cycle which is used to calculate the efficiency of the heat engine when a heat engine returns to its original state after passing through a number of successive specified thermodynamic change is called Carnot cycle. Conditions for Carnot cycles. The Carnot engine chosen for the purpose is hypothetical one. It is also called reversible heat engine because all the operations in the cycle are done by using 1 mole of an ideal gas in a cylinder behaving weightless, frictionless piston under isothermal and adiabatic conditions at the different time. The Carnot engine has following main parts: a cylinder, an insulated non-conducting material through which heat transfer is not possible, 2 heat reservoirs. One is the hot reservoir at high temperature where the heat capacity is infinite so that the temperature of the hot reservoir remains constant even after losing one amount of energy from it, and the other is the cold reservoir at low temperature called the heat sink whose heat capacity is also infinite so that the temperature of the cold reservoir remains constant even after taking any amount of energy from it. Fourth is for isothermal expansion. The cylinder is put on the source so that the exchange of heat can take place. Here heat flows from hot reservoir to gas, which results in expansion of gas. For example, that is volume increases and pressure decreases. As whole, the heat is used in the expansion of gas, so the temperature of gas remains constant. dt is equals to 0, dE is equals to 0, dH is equals to 0, dQ will be positive and ds is equals to positive. For isothermal compression, the cylinder is put on the sink so that the exchange of heat can take place. Now press the piston downwards, which causes compression of gas. The heat released due to the compression of the gas flows from gas to cold reservoir. So the gas compresses at the same constant temperature, volume decreases and pressure increases. dt is equals to 0, dE is equals to 0, dH is equals to 0, dQ will be negative, ds will be negative. For adiabatic expansion, the cylinder is put on the insulating material so that no exchange of heat can take place because of the gas cylinder is confined by non-conducting wall. Now let piston rise slowly upwards, which continuously results in the expansion of gas, that is volume increases and pressure decreases, and it occurs by using internal energy of gas molecules, so the temperature of gas decreases. dt is equals to negative, dE is equals to negative, dH is equals to negative, d theta is equals to 0 and ds is equals to 0. For adiabatic compression, the cylinder is put on the insulating material so that no exchange of heat can take place because the gas cylinder is confined by the non-conducting wall. Now let piston press slowly downwards, which continuously results in the compression of the gas, that is volume decrease and the pressure increase, and it results in the release of energy which is absorbed by the gas molecules, so the temperature of gas increase. dt will be positive, dE positive, dH positive, dQ will be 0 and ds is equals to 0. The terms of the enthalpy change of system. T delta S SV will be greater than equal to dE plus P dV. T delta S of system will be greater than equals to dH minus V dP. Delta S is equals to 0 and delta P then above equation will be 0 is greater than or equal to dH or dH sub S or P is less than 0. Entropy change for an ideal gas with change in pressure, volume and temperature. Suppose an ideal gas undergoes a reversible isothermal expansion on absorbing small amount of heat, and thus the entropy change is given by ds is equals to SQ reversible iso upon T, dE plus PdV upon T, at Cv is equals to dE upon dt. Tds is equals to dE plus Pdv is equals to Cv dt plus Pdv. Tds is equals to Cv dt plus RT upon V dV. Divide the above equation by T and integrate the following limitation, and we will get delta S is equals to Cp ln T2 upon T1 plus R ln P1 upon P2. At constant temperature, equation first will become delta S is equals to R ln V2 upon V1 is equals to 2.303 R log V2 by V1, and at constant temperature equation 2 becomes delta S is equals to R ln P1 upon P2 will be equals to 2.303 3 log V2 by V1. At constant volume, equation first will become delta S is equals to CV 2.303 log of T2 upon T1. And at constant pressure, equation second will become delta S is equals to 2.303 Cp log T2 by T1. Let G1, H1, S1 be the free energy enthalpy of entropy of R, and let G2, H2, S2 be the of P. Thus, G1 is equals to H1 minus TS1, G2 will be equals to H2 minus TS2. Subtract equation first from equation second, and we will get G2 minus G1 is equals to H2 minus H1 minus T S2 minus S1. Delta G will be equals to delta H minus T delta S, gives the third equation. Delta G, free energy change of the system. Delta H, enthalpy change of the system. Equation 3 is called the Gibbs free energy equation. Physical significance of Gibbs free energy. From first law of thermodynamics, delta E is equals to Q plus W. Delta E is equals to Q minus W exponential plus W useful. Delta E is equals to Q minus P delta V minus W useful. Delta E plus P delta V is equals to Q minus W useful. Delta E plus P delta V is equals to T delta S minus W useful. Delta H is equals to T delta S minus W useful. Delta H minus T delta S is equals to minus W useful. Delta G is equals to minus W useful. Minus delta J is equals to W useful. That is, the decrease in the free energy is measure of useful work done during the change. Decrease in the free energy change is the cause of the spontaneity of the reaction. That is, the decrease in the free energy, it means useful work done during the change. Decrease in the energy change is the cause of spontaneity of the reaction. Variation of Gibbs free energy with temperature and volume. The free energy is given by G is equals to H minus Ts. H is equals to E plus PV. G is equals to E plus PV minus Ts. Do differentiation dG. After differentiation, we will get delta G is equals to nRT log P2 by P1, or delta G is equals to nRT log V1 by V2. Third law of thermodynamics. It states that at absolute 0 Kelvin temperature, the entropy of the perfectly crystalline solid becomes 0. It is based on the generalization based on the experiences, and there is no direct profession of law. Application of third law of thermodynamics. It helps in the calculation of the absolute entropies of the substance at any temperature. The entropy change of a reaction can be calculated as ds, and we will get ds is equals to dH upon T, that is Cp dt upon T. Cp is equals to Q dP upon Q dt. Integration of ds from limit S1 to S1 to S2 will give Cp integration of dt upon T limit from T1 to T2, and we will get S is equals to 2.303 Cp log T. The above equation helps us to calculate the value of S directly by knowing the value of Cp and T. Note, if a substance is gas at 1 atmospheric pressure and 25 degrees Celsius temperature, then the entropy of a gas at 25 degrees Celsius temperature will be equal to the sum of the entropies involved in the different stages. Test of third law of thermodynamics. Calculation of Gibbs free energy. Delta G naught is equals to delta H naught minus T delta S naught. The delta G naught can be calculated by knowing the delta H naught value and absolute entropy from third law of thermodynamics. Calculation of equilibrium constant. Delta G naught will be equals to minus RT log K. Limitations of third law of thermodynamics. Exception of third law of thermodynamics is CO, NO, N2O, Cl2O solid has some entropy even at absolute zero. This entropy, which is present in substance even at the absolute zero, is called the residual entropy. Thank you.